Hello everybody. Welcome back to another installment of some physical chemistry knowledge nuggets, as I like to refer to my the videos that I make, little bits of knowledge, right? So here you go. Have a knowledge nugget for your wonderful Wednesday. Yeah, as you probably are aware of by now, classes are continuing today, even though it is wonderful virtual Wednesday, and that's just because we ran out of we had that extra week of spring break, and a lot of us are trying to fit the information in that we kind of lost out on by having that extra week of spring break. I understand that was through no fault of your own, also through no fault of our own. It's just the way the cookie crumbled. So rather than cry over spilt milk, we're going to continue. Man, how many phrases can I throw into one day? Okay, let's continue with thermodynamics. We came up with this expression here that allows us to relate the delta S for a phase transition with the delta H of the phase transition, and it's divided by temperature. Okay, that's a pretty useful expression, but what else can we do? I'm sure that we can find other useful little tidbits if we just look hard enough. Okay, so what else can we find? At equilibrium, above when we were deriving this expression here, we came up with an interesting observation, and that was that at equilibrium, the chemical potential for the phase 1 is equal to the chemical potential for phase 2, right? So if we rearrange this a little bit, we can see that the chemical potential of phase 2 minus the chemical potential of phase 1 is equal to 0. What does this look like to you guys? This is a delta mu. So if we say delta mu is equal to 0, right? Or what's also true in this case is the infinitesimal change in mu is 0. Okay, so d mu is 0. At equilibrium, what else is 0? What else is 0? Well, dg is 0. Right? Delta G and dg are equal to 0 at equilibrium. So therefore, we can set the infinitesimal change in mu is equal to the infinitesimal change in g is equal to negative s hat dt plus volume hat dp. Okay, and this, of course, is only at equilibrium. Okay, so d mu is equal to negative s dt plus v dp. What is this actually saying here? So if we have an infinitesimal change in t and an infinitesimal change in p, we can relate that back to the phase change. We can relate that back to an infinitesimal change in t and p. Okay? And when we have an infinitesimal change in t and p, so say we have a dt and a dp, what happens to the system? The system re-equilibrates so that the mu of phase 1 is equal again to the mu of phase 2, right? So again equilibrates. Right, due to as Le Chatelier put it, his principle, Le Chatelier's principle, a system at equilibrium tends to stay at equilibrium unless it is acted on by an outside force. And when it is acted on by an outside force, that system seeks to find equilibrium again, and it does that by changing the phase. Okay, so there is an infinitesimal change in phase that's related to these infinitesimal changes in temperature and pressure. Okay, so again, after this, we're going to have mu phase 1 is going to equal to mu phase 2 again, and this is going to come about because of some infinitesimal change in the mu of phase 1 and an infinitesimal change in the mu of phase 2. Okay, so because of all of this, we can actually say that the infinitesimal change in phase 1 is equal to the infinitesimal change in phase 2. Right? They're both changing. They both have to equal. They both have to change in an equal amount. So you can say that the change must equal one another. Right? So because this is true, right? Because this is true, we can use this and this expression up here, and we can form a new expression that starts with negative S for phase 1 dt plus the molar volume for phase 1 dp is equal to negative entropy, molar entropy of phase 2 dt plus molar volume of phase 2 dp. Okay, interesting. Now these guys here, we can just, well, actually, sorry, nope, getting ahead of myself. I'm going to rearrange this so I have the entropies and the volumes on one side of the equation, and the so I have the entropies on one side of the equation and the volumes on the other side, and this is going to end up looking something like molar volume for phase 2 minus molar volume for phase 1 multiplied by dp is equal to the molar volume for phase 2 minus the molar, not volume, the molar entropy for phase 1 times dt. This part here and this part here are just delta V and delta S, right, between the two phases. So we can rewrite this whole bit as delta V dp is equal to delta S dt. If I take delta S, or delta P and delta dt, blah, 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 dp and dt on the same side of the equation, I end up with dp over dt is equal to delta S hat over delta V hat. Okay, so here we are relating the entropy, the change in entropy of a system, the change in volume of a system, directly with the change in pressure and temperature. This is sometimes less formally written as delta P over delta T is approximately equal to delta S molar over delta V molar. Okay, and this is called, both of these together, in whichever form you use them, are called the Clapeyron equation. Wow, that's a really bad. Clapeyron is C-L-A-P-E-Y-R-O-N. Clapeyron. Good old Benoit Clapeyron. I have no idea. He was a French guy. I have no idea if that's actually how you pronounce his name, but I'm going to go ahead and guess that it's very similar to that. And the Clapeyron equation is very useful. It's extremely useful. And it's useful because it's, for number one, it's applicable to any phase equilibrium. Okay, so it's applicable to any phase equilibrium. And just looking at it, it's rather useful. It allows you to estimate the pressure change necessary to shift a phase equilibrium at a given temperature. Okay, so if you have some given temperature and you want to see how much pressure you have to put in or take out to instigate a specific phase change, you can do that simply by using the change in entropy and the change in volume for the system. Let's actually do an example of this. There's a fun example in the book, and it is essentially, the task is given to us to estimate the pressure necessary to make diamonds out of graphite. Diamonds out of graphite at a temperature equal to 2,298 Kelvin. Okay. Now, diamonds and graphite. Now, of course, you know that they are both made out of solid carbon. So we have carbon on one side, solid in graphite form. And we also have carbon as a solid in diamond form. Okay, these together are called allotropes. Okay, allotropes. They're made of the same substance, but they have a different solid phase. That's what an allotrope is. Same substance, different solid phase, and transitioning between the two. So say we can go from graphite, which is what we're supposed to do in this problem, solid, into diamond, solid. This is a phase transition. Okay, it's a phase transition. Even though you're going from solid to solid, it's still a phase transition because you're changing the allotrope. Okay, so you're going from one solid form into another, and so we can still use this Clapeyron equation above to calculate the pressure change that's necessary to actually force this reaction to occur. To do this, though, we need some numbers. So if we have the molar entropy for each of these systems and the molar volume for each of these systems. So let's do carbon here, S graphite, and carbon here, S diamond. The entropy, the molar entropy for solid graphite is 5.69 joules per Kelvin. And these are things you can look up in a table. And for diamond, it's 2.43 joules per Kelvin. The volume that's taken up can be deduced from the density of these two systems. So you can look up the densities and basically take a ratio and come up with these numbers. So that's 4.41. Change in volume between a certain amount here and a certain amount here would go from 4.41 times 10 to the minus 3 liters to 3.41 times 10 to the minus 3 liters. Okay. Now we can set this up. We have this equation, our estimation equation. Delta P over delta T is approximately equal to delta S over delta V. We can rearrange this and solve for delta P. Delta P is equal to delta S times delta T over delta V. Okay, so we just need delta S, delta T, and delta V, and we can find the change in pressure. So delta S is equal to the final pressure minus the initial pressure. So we're going from graphite to diamond. So the final entropy is 2.43 joules per Kelvin minus the initial entropy, which is 5.69 joules per Kelvin. And we end up with negative 3.26 joules per Kelvin. Okay, now delta V we can calculate in the same way. Final volume is 3.41. Initial volume is 4.41 times 10 to the minus 3 liters is equal to, let's see, that's negative 1, right? Negative 1.00 times 10 to the minus 3 liters. Okay. Next, delta T. Delta T, so all of these numbers, by the way, any type of number that you look up in a table is typically given at 25 degrees C. Okay, so the difference in pressure between the two usually comes from the difference the difference in temperature usually comes from room temperature to whatever temperature you're given in the problem. In this case, the temperature we're given is a 2,298 K. So the final temperature, 2,298 Kelvin minus 298 Kelvin, or 25 degrees C, gives us a delta T of 2,000 Kelvin. Okay, now we have delta P. We can plug in these numbers. Negative 3.26 joules per Kelvin divided by negative 1.00 liters. Times 10 to the minus 3 liters. Multiplied by delta T, 2000 K. Let's see, Kelvins cancels out. Now we have joules per liter. I want to transform these into some sort of pressure unit, so I'm going to multiply it by 1 liter bar is equal to 100 joules, our conversion factor there. And then liters cancels out, and I'm left with bar. And I end up with, let's see, what is it? 65,200 bar. Which is a huge number. Okay, so atmospheric pressure is about 1 bar. It's about 1 atmosphere. So this is 65,000 times atmospheric pressure. Okay, 65,000 times atmospheric pressure, which is an absolutely huge pressure. That's why this type of thing only happens naturally, very, very deep under the Earth's surface in these high pressure systems that are found by tectonic plates colliding with and rubbing against each other and forcing these systems of extreme pressure. That's why you have certain regions of the world that have a high concentrations of diamond, and it's all because of geological activity in that particular area has allowed graphite, which is essentially fossilized carbon sources, to turn into diamond over time. Okay, you have to have extreme temperatures and extreme pressures, and then you form diamond. Pretty cool. And the Clapeyron equation is allows us to be able to estimate those pressures. This is whoops, I wrote 65 times. It's 65,000 times. Okay, 65,000 times the atmospheric pressure. Okay. Can we find a different form for this, right? Can we find a different form? Something perhaps that relates delta P to other useful or easily calculated values, for example, delta H. Okay, can we have other forms of this, of the Clapeyron equation? And the answer, of course, is yes. If we take delta S trans for the transition, we know that that's equal to delta H for the transition divided by the temperature. Okay, recall this from earlier. We derived this, I think it was the last meeting actually. Okay, and we're going to take this delta S here and we're going to substitute it into the Clapeyron equation. I'll just call that the clap. Do you have the clap? The further we get into this virtual world, the more and more loopy I'm going to get. It's just the way of the world. So be sure to stick around, because I'm sure that it's going to get even weirder. Okay, so I'm going to substitute that into the clap, and I'm going to do a bunch of math behind the scenes. I'm not going to actually show this here because you guys get the point. We've done so many of these derivations that you kind of see where this is going to come from, okay? And if not, you can go through and actually look through the derivation yourself, work it through yourself. But essentially what we end up with is a relationship between delta P and delta H. So we have delta P is equal to delta H, molar actually, delta H over the delta V times the natural log of the final temperature over the initial temperature, okay? So it's not just delta H that we can relate this, or delta S we can relate this to with the Clapeyron equation. We can also relate the change in pressure of a phase transition with the change in the enthalpy for that relation, or for that transition. Okay, so this, so far we've kind of left, we've tried to treat all systems identically. So saying, all phases fit within all of the math that we've come up with so far, okay? But if we start to go towards gas phase or, condensed phase, we can begin to make approximations to these thermodynamic principles that allow us to make certain rules that only apply, for example, to gas phase reactions or gas phase interactions. Okay, so let's talk a little bit more specifically now. These have all been very general above. How about the gas phase? What happens in the gas phase? Can we make any simplifications that allow us to come up with generalizations for the gas phase? Okay, and the answer, of course, is yes. Of course, we can make simplifications. That's why we're doing this. And the biggest and most obvious simplification comes from the volume, right? In a condensed phase, the condensed phase volumes are very, very small. So they are tiny in comparison to the molar volumes of the gas phase. Okay, so when we talk about delta V, right? Delta V is equal to V2 minus V1, right? If we have a gas phase volume in here somewhere, the gas phase volume is going to completely dominate delta V. So that's, because of this, we can completely neglect the molar volume for the condensed phase. And we can write delta V as just the V of the gas. Okay, so if we substitute in, so we have dP over dt. Oh wait, I didn't write this out. Yeah, I didn't write this out. Wait a minute. 1 second, I need to collect my thoughts. Okay, so essentially within this whole math step here, there is a point that we get to where we have dP over dt is equal to delta H bar over R over T times delta V, okay? And actually this is pretty simple to see if you just plug in this delta S trans into the above equation, okay? So we can write dP over dt is equal to delta H bar over temperature times delta V bar, right? But since we're saying that V condensed is tiny in the gas phase, we can completely neglect it, and we can say that this dP dt is now equal to delta H bar over T times V gas, okay? Now, if we assume ideal, right? If we assume ideal, we have a state function that goes with this volume for the gas, and we can write that as this molar volume of the gas is equal to RT over P. Oops. RT over P, and we can plug that guy back in, and so we end up with dP over dt is equal to delta H bar over temperature times RT over P. After a little simplification, this becomes dP over dt is equal to delta H bar times P divided by T squared times R. Now, I want to get the variables on the right side. So I want to take dt and move it over here, and I want to take dP and move it over here. Okay, so after a little rigging, this ends up being dP over P is equal to delta H bar over R times dt over T squared. Okay? Now, dP over P. I'm going to write this in kind of a weird way, and you have to recognize, to understand why I can write it this way, is the derivative of the natural log of P is equal to 1 over P. Okay? So think of it that way, and I'm going to rewrite dP over P as d ln P is equal to, next page, is equal to delta H bar over R times dt over T squared. Okay. Now this is one way to write this equation. It's a very famous equation. I think that the easier way to understand this is by taking a derivative of both sides. Okay, so if I take the derivative between one pressure, or between P1 and P2 of d times the natural log of P, this equals to the integral from T1 to T2 of, let's see, delta H bar over R times 1 over T squared dt. Okay, I take those two integrals and I end up with the natural log of P2 over P1 is equal to negative delta H bar over R times 1 over T2, T2 minus 1 over T1. Okay, so this is a famous equation. It's called the Clausius-Clapeyron Equation. Okay, the Clausius-Clapeyron Equation. I think it's more famous in its integrated form than it is in its normal form. I certainly like the integrated form a little bit better. It's easier for me to understand. And this is an incredibly useful equation. Okay, incredibly useful equation. As a matter of fact, there are two examples where it shows you how useful this equation is. Example 6.7 and 6.8. Essentially, what this equation tells us is what temperature is necessary to create a specific equilibrium pressure. Okay, so what temperature do I need in order to create a specific equilibrium pressure? Now, this should start to ring some bells in your mind, right? Because we actually used this concept when we did our adventure on the mountain. Remember when we went up Roan Mountain and we measured the boiling point of the liquid, of the water as we went up the mountain, and we saw that the boiling point actually decreased as the pressure decreased. So we were directly measuring the atmospheric pressure using this relationship right here. Okay, and then there's another relationship that comes in with the vapor pressure of the liquid. But yeah, I'm not really going to get into that. The book goes into it in a little bit more detail. So if you're interested in how this relates to the vapor pressure, check out the end of, I think it's section 6.7 or 6.6 maybe. It gets into how this relates to the vapor pressure above a liquid. So super interesting. We finally got to the point where we're describing the physics behind that lab that we did where we drove up the mountain. Okay, and I'm going to stop there for today. I will start back there on Friday. Let's see, what's today? Wednesday. We'll start back there on Friday. Oh, actually, no, you guys have an exam on Friday. Right. Okay. Right. So exam on Friday will basically be at the exact same time. I gave you guys some information on that exam, like on the actual exam that I posted on Canvas. But just to reiterate, it'll be a 2-hour ordeal. You guys will have 2 hours to do the exam, and then scan it and submit it back to Canvas. So I'm giving you a little bit of extra time because I know that scanning and printing and, you know, all that stuff can sometimes lead to issues. So I will upload an exam file at exactly, I think I'm pretty sure it's at 1 p.m. I don't know. I have the date or the time written on the exam on Canvas. So just go check there for the exact time. But I'll be posting the file, and then you'll have 2 hours to complete it and then resubmit it. Okay? So don't forget about that. Also, I changed the due time or the due date for the homework that was supposed to be due today. Some people are having trouble with it. And I just wasn't able to get to the point of being able to help you guys with that homework yet. So I've extended that due date to tomorrow at 5 p.m. And hopefully in the meantime, I'll be able to pick up on that. Okay? Yeah, so if you have any questions on the homework or on the exam, feel free to email me. Other than that, I hope you guys have a great rest of the week. I hope the exam goes well for you. Yeah, and have a good weekend. And I will see you same time, same place next week. Take care.